So welcome back. So this video is a combination between simple harmonic, which is oscillation motions, with the conservation of energy and momentum. So basically I'm trying to prepare you for the AP exam. This is how it is done. 3 different concepts together. So let's go ahead and look at what we need to do in order for us to use some of the information from the earlier part of the lessons to calculate this for the second part. Okay, so go ahead and look at this graph and compare this one with this one. So basically I have 2 different experiments that you have to kind of mix it a bit and understand what's going on. So basically we have a box, same. And now at this point, the box itself is being compressed at a certain D, which is exactly the same thing as the X is displacement, it's the same thing. And look at the graph. So basically what would happen when you actually, either you pull or you compress with the same distance, so, and with the same constant, everything else is the same. So basically we pull this one and we let it go. Then it will actually oscillate back and forth, back and forth, back and forth without losing any velocity or without losing any energy due to the frictions. So this is how the graph is going to be. You see how it is? Stop right here, there's 1 cycle, there's 1 period. And the time it takes should be 0.7. And go over here, that's another 0.7, since this one is an ideal one. So as you can see, the maximum velocity is the same throughout the oscillations. But what would happen in the second experiment, since you can see now the block itself and the spring is placed on the rough surface, which by all means from Newton's second law of motion, which involve the frictions. That's why I put mu there, because you're going to have to figure out to use the mu or the friction to calculate what it is. And now you're going to have to identify the free body diagram of the box. So we're going to go back and visit it. The third lessons, which is Newton's law of motion, which is basically free body diagram, which is going to be every single one of the tests. You have to be able to draw that one. So let's just go ahead and figure out the second experiment first. You do the same thing. First, it starts out with the same one. As you can see, it reaches the maximum velocity and it comes to rest. Same. As you can see, the more it's oscillating, the friction is do the work. The friction will do the work, so as a matter of fact, the velocity is being decreased, until all the end that there's no movement involved, because the friction does all the work in order for that box to stop moving or stop oscillating. So let's just go ahead and draw a free body diagram of this box right here. For example, right, if the box is moving this way toward equilibrium. So we're going to have to utilize it in the second law of motion again. The object itself is on the surface, therefore there must be a force due to the gravity. And also there is another force upon it, which is the normal force. This is 2 other forces that you need to have in order for the object not to be moving up and down. So the arrow, which indicate the vector, has to be the same. Then the spring is pushing that one, so the force is going that way for the force of the spring. And over here is the force of friction. Because the object itself is moving that way toward the equilibrium position, so you're actually moving toward this line right here, so the spring is pushing that way, and the frictional force, which is the force acting upon the object in the opposite direction. Therefore, this is it. This is how you would apply the second law of motion to these systems. So now let's get back to our task, is to solve for constants. If you don't know what constant is from this experiment, we can solve for the K, which is 2 different equations. So if you want to do the easy way out, here is equal to K divided by M, right? But I need to get rid of this square. That's why I'm square both sides of the equation. So my K is equal to omega squared multiplied by mass. Let's go ahead and substitute the values. This one from original one, which is, let's get back. Okay, let's look at what we had for that one. It is actually a 9. Let's double check again to see what it is that we came up with. It's actually 9 squared multiplied by the mass in kilogram, which is 0.3. So when you square that and multiply by 0.3, you should be able to figure out what the K constant in this case. So the answer would be 24. Okay. This is one way you can solve for it. So there's another way that you need to solve for by using this equation. T is equal to 2 pi mass divided by K. So like what we would do to get rid of the square root, you square both sides of the equation. So in the period square 4 pi squared m divided by K. So we're looking for K's. That way I'm rearranging everything, so every 4 pi square mass divided by period square. And then all you have to do is just plug in the number. 4 pi square. What's our mass? 0.3. Divided by our period. What was our period again from the graph? So basically the period, we get it from this one right here. So it takes 0.7 seconds. That's what the period is. We put it in there, 0.7 seconds squared. And to go ahead and do the computation, solving the problem. So we need the answer. We need to find it. So the answer is 24. This is your K, this is your spring constants. So as you can see, it's the same way. It's either using the two different equations. It depends on what they're given. If they're given the omega, which is what you get from the graph, which is 2 pi. If they are basically, if they are given the period, then you can solve for this. Same way. This one you given the period. So if they were to be if you were to be asked to solve for period, that would be an easy way out. All you have to do is multiply this number and plug them in. I'm just gonna show you for the next video to see how simple it is. For this video, I'm just gonna go ahead and explain all the important or hard concept first. So now, go ahead. We're gonna have to figure out how to use this concept right here to apply to this system. So basically, this is what happened. You actually pull it, and it will actually start oscillating, right? And then what happened in this one is that the string is cut. So the box, we're actually gonna go there and release and goes with a certain velocity. And you know the displacement where you push it. In this case, let's go back to what we have for the maximum displacement. It's given 0.018 meter, which is basically 1.8 centimeters. So now you know what K is. 24. What is our x squared, which is just that 0.018 square. Mass is 0.3. And this is V squared. So basically, I'm doing this to solve for v squared. And whatever the answer I have from here, so for this one, I'm just gonna go ahead and put all the number in since I don't have the calculator with me. Once you square that, that will be your initial velocity, which is gonna be labeled as this one, which is that one.